Okay, so RC circuit review. Yeah, not remote control. So if I have a 15 volt let's pick this as 1 microfarad, 1 kilo ohm. If I hook this up, okay, just a note for the lab. The center goes here so you don't accidentally short power to ground.
Yes.
I'm right here and I've been there for a while, so my capacitor fully drains. I move this up at time 0. Quick snap questions. At t equals 0, a lot of times mathematically we'll put a little plus. So t0 minus is the instant 0 when it hasn't connected, and t0 plus is the instant 0 when it's connected. So I have a complete circuit. What things happen here? Okay, capacitors don't allow an instant change in voltage, right?
Yeah.
So therefore, my battery voltage is 15 volts. My capacitor voltage is 0 volts. My resistor voltage is
15.
yeah. I have a complete circuit. So just because there's no voltage on that doesn't mean there's nothing here. That means my current is 15 milliamps. What's happening? We will talk about current at times flowing through the capacitor, but of course no current's flowing from one plate to the other. What's happening is we're stripping charges off, moving them through here at 15 milliamps. 15 millicoulombs per second are being moved from that side to this side. And as it moves, what happens is the charge builds here. We have a voltage proportional to the charge. When this voltage ends up at 15 volts, then I'll have 0. So after some time, battery voltage is still 15 volts because it's a battery. Capacitor voltage is fully charged to 15 volts. The resistor voltage is 0 volts, because these two have to add to 15, and therefore your current is 0. It just sits there. How long is this?
It's like 10 time constants or something.
5 time constant. 5 tau, which is 5 times RC, because tau is RC, which is 5 times 1 kilo ohm times 1 microfarad, which looks like it's going to be 5 milliseconds, if I do the mental math correctly. Let me double check it. So 1 times 10 to the 3 times 1 times 10 to the minus 6 should be 1 times 10 to the minus 3 times 5. However, I can also use my calculator. 1,000, 1 times 10 to the 3 times 1 times 10 to the minus 6 times 5. Yep, 0.005 seconds or 5 milliseconds. I don't want to build that because, well, my eyes aren't fast enough to observe it. You'll probably just look at the random stuff on your Okay, so I have a time constant conveniently of 1 millisecond. So let's try something like that. Hey, at. You remember what the percentages are?
39.4, 63.2, 77.7.
Yeah, I thought the 63 was.
I could have sworn that one was the first time constant.
Yeah, I thought that was 63%.
Maybe, I mean, this thing, it has 10. So maybe it's 63.2, 86.5, 95, 98.2, 99.3, 99.8. Maybe. Because this one's got 10 boxes.
Yeah, 63.2% after 1 time constant.
Okay.
So one-time constant 63%, 2 is 86%, 3 is 95%. That's one I usually remember. 3 is 95.7. This 3 is 95% of the way there. 5 is 99 point something percent of the way there. So that's basically where we say it's fully charged. Mathematically, it's an asymptote, so it never actually gets there.
I was about to ask that.
Yeah. If you ever wonder where that comes up, yay, asymptotes. But 5 time constants in there. All right, so let's try this. After this, the battery voltage is, of course, 15 volts. The capacitor voltage is 63.2% times 15 volts, which is whatever that is. So 0.632 times 15 is 9.48 volts. So after 1 millisecond, we're almost 2/3 of the way there. So the resistor voltage is 5.52 volts. The current I can pick the percentage for any of the others. And I do, yes, on the lab, I ask you for ones in between, and you're gonna have to go, I don't give them to you directly, but you have that curve, don't you, that I gave you, the curve, I put it back out there, but I think I put it this one. I think it's a little curve that shows you charging and discharging, and it shows you what they are for 1, 2, 3, 4, 5 time constants, 1, 2, 3, 4, 5 time constants.
Yeah.
If you got 10 spots, you actually have to do half a time constant. So what you have to do is go up half, kind of trace it up on that, and find what it ought to be. So it'll be less than, it'll be more than 0 and less than 63.2%. Probably much closer to this.
What I did is I would just connect the multimeter to it and then record.
Yeah, but when you do the theory, you need to pull them off here.
Oh, right, yeah.
Yep. When you do the actual measurements, you just have a percentage.
Yeah.
All right. Does this all make sense? This is all coming back now? All right. So now what I'm going to do is I'm going to erase this stuff. It's been like this for a while, so it's fully charged. And then we'll just start our time when we move the switch. We'll move the switch down here. So the battery's disconnected. So that at the instant we move the switch, the battery voltage is 15 volts, but who cares? It's not connected to anything. The capacitor voltage cannot instantly change because it's got a bunch of charge sitting on this plate of the capacitor. In theory, if I totally disconnect the capacitor and take it away and don't touch the ends, let anything drain, I'll measure it, it's still 15 volts. So just sit there and hold it forever. Real capacitors will sit there and hold it for a while. When you're doing this experiment, you frequently have to sit there and touch something across the 2 ends to make it drain off so you can move on. So what's the voltage across the resistor then?
0.
No,
15.
because this is a complete circuit now. So if that's 15, so resistors can change voltage immediately. So right now, when we do this, that's 15 volts, it's been fully charged. So I'll start pushing a current that way. So the resistor voltage was 0 before this touched. As soon as this touches, then instantly there's voltage across resistor. That's a complete circuit. Now the supply is what's sitting across the capacitor. And what will happen now is because it's positive, this is negative, the positive would like to come over here. It will just start going through the resistor. So my current, the instant I switch there, it's going to be 15 over 1 kilovolts, so you get 15 milliamps. So after a minute, so it's been a while, voltage across the battery, I know, not even part of the circuit. It's just sitting there. Voltage across the capacitor, it's fully drained. Voltage across the resistor, discharge. Same time constant because it depends on RC. I'm gonna just keep writing this just because it's sitting there on there. So the capacitor voltage is drained
Of 15.
1 minus, or that was 63%. They'll tell us over there, what is that, 37%? Because it's gone 63% of the way down.
Yeah.
So we'll actually be at 37% of its initial voltage.
Yeah.
So we'll drain all the way down to 5.55 volts. That means the voltage across the resistor, since it's the only thing that can be dropped in that voltage, is 5.55 volts. Therefore, the current is 5.55 milliamps. So also be careful when you're charging, the capacitor voltage would be following this charging. The resistor voltage will actually be following this because it starts maximum and goes down. And the current will be following this because it starts maximum and goes down. When you're discharging, everybody's going down. Okay, we're not going to do it live, but we need to understand it. RL, or L over R. So I'm going to come in, I'm going to replace this thing. With a 1 millihenry inductor. We're going to go back to it. It's been here for a while, time 0. We go up there. First of all, it's our time constant. L divided by R. So 1 millihenry. Actually, let me make this a big number. 100 millihenries. 100 millihenries over 1 kilo is 0.1 henries over 1,000 ohms, which is unfortunately really tiny. Well, this is why we don't do the inductor one quite as readily, because I need it. 100 millihenry is my biggest inductor in here. With 1 millisecond, so 1,000 microseconds, 100 microseconds. So, for example, if I wanted this to have a time constant of 1 second so I can see it, I'd need like a 100 milliohm resistor, which would put lots of current through the resistor, and then I'd have other problems. So, you had to play with it last week combined with the capacitor. All right, anyhow. So, capacitors or inductors do not allow an instant change in current. The current was 0 before I closed this, therefore the current is still 0. That means the voltage across the resistor is 0 because Ohm's law. If I know either of these, I know the other because Ohm's law. Ohm's law does not apply to inductors, therefore all the voltages get dropped across it. So inductor will have 0 current and maximum voltage and then they'll cross. So after a while here, my inductor will end up with 0 volts. I'll get all 15 across the resistor, so there's 15 milliamps. When they're sitting there working and they're fully charged up, inductors are just like a short circuit. All there is like a wire. And all they're going to do is prevent instant changes in current. They're going to make it always take a while. It takes a while when you flip the switch for the current to ramp up. It'll take a while for it to ramp back down. At 200 microseconds, so 2 time constants, we're 63% for all this. Of course, the battery voltage is 15 volts. So the current now is going to be 63% of its final, oh, why did I write millihenries? Milliamps, okay. It's gonna be 0.63 times 15 milliamps. So I've gone to 0 up to 9.45 milliamps. And now I can do Ohm's law, that times that. And up here, I'm gonna have 5.55 volts. Just those two have to add to 15. Good with all this? My inductors work the same as it calculates the time constant. Well, I should say work the same. You have to pay attention to this detail. Okay, if you recall, this voltage on the inductor is the inductance times how fast the current's changing. So when the current's no longer changing, there's no voltage. When the current's changing rapidly, there is voltage. Okay, let's try discharging real quick, and then I'll let you go. There we go. Okay, in that case, it's been sitting there a while, so we had a constant 15 milliamps, constant 15 volts crossed here, and 0 volts before the switch closed. Now the switch closes, no instant change in current, which means there's no change across the resistor voltage. But this voltage has to immediately jump up to 15 volts because that's my circuit. In this case, the current's still going the same way. So the resistor is just holding the voltage going and our current going. It's just going to take a while to ramp down. After a while, we're going to dissipate. If I go at 200 microseconds, then that means my current is 1 minus 63%, 100 minus 63, times 15 milliamps. The number that looks similar before. So 37% times 15, 5.55 milliamps. So after 2 time constants, I will have gone from 15 milliamps down to 5.55 milliamps. Ohm's law. Whatever's left over is across the inductor. So this is going to take a while for the current. So I close, all what's happened is all the energy held in this magnetic field is now being turned back into current. Just keep pushing the current until it runs out of energy and the magnetic field is done. After about 500 microseconds. So time. Anything else on these? They'll be more interesting when I put them in AC circuits because the AC voltage always changes. It's alternating, which means current always changes, which means my inductors and capacitors are reacting to this constantly changing voltage and current, so they never get to settle down and be blowing. They just keep doing things. But next semester. The other thing you can do is the following. This is called a tank circuit.
The tank circuit.
Yeah. It's like a water tank. Alright, I can do this. Close that. 15 volts, 1 kilo ohm. Instant I close that, no instant change in voltage, so these stay 0. Takes a while, no instant change in current, so there's no current there, but there is current here. As this voltage changes up, we'll start to get current in there both. Okay, it'll fully charge up. Eventually what's gonna happen is I'll end up with 15 volts here. This is in parallel, so that's 15 volts. Okay. We have current going through here, not one here. Then I'm going to disconnect it. So this is all off there, and what do I have here? No instant change in current, no instant change of voltage. So my current will go around these two, this current that's being held there, which would have been 15 milliamps the instant I close it. And it'll just sit there. And what's going to happen here is we're going to start at 15 volts. We're going to drive this current. And we're going to go. And we're going to start moving the energy back and forth. So I move all the energy in the electric field. None of it's over here pushing current, and then we have 0 volts, or 0 amps flowing through it. And then what happens? Oh, this doesn't allow an instant change. So the magnetic field reverses direction, and the charges start going the opposite direction. So what's going to happen here is, I'm going to erase those because we keep going. We'll end up going from 15 to 0 to minus 15 to 0 to 15 to 0 to minus 15 to 0 over time, because the energy will build fully on the capacitor and then stop, fully charged. But the inductor says, nope, I'm not going to let current stop. So the capacitor just changes direction to keep pushing current. And then we'll completely drain the capacitor so we have 0 voltage across them and a maximum current, which can't stop. So it starts building the charges up on the capacitor, opposite polarity, as it drains. So what happens effectively is all the energy goes from the electric field, maximum, into the magnetic field, into the electric field, reverse direction, into the magnetic field, reverse direction. There's no resistance because these are all ideal. So it sits there forever, and the energy just goes back and forth between them. The idealized version of this is like a perpetual motion thing. Now, of course, these have real resistance, so over time they'll lose its reality. But it sits there for a long time. How quickly will this go back and forth? 1 divided by 2 pi, square root of the inductor times the capacitor. That will determine how fast that energy goes back and forth, because it's like a sine wave. But it's really the DC circuit where we just have a capacitor and inductor connected together. Now, if I took that and I took my and ran an amplifier with negative feedback into it, I would drive that, and I could take that ability to keep reversing direction and produce a sine wave out of it. So we'll do that in semiconductors. Okay, I'm done. Let's get questions. So this week, go build those RC circuits and have fun with them. It's a good chance to practice and turn in pretty graphs. So recall last semester, you liked doing the graphs. I don't know if you like doing them now, but you've learned that